As we speak, the sounds of our voices are carried through the air as vibrations. When these vibrations reach a microphone, they are recorded, and in digital audio recording, the sound waveform is sampled several thousand times a second. These samples make up the final waveform as interpreted by the computer. But what if we took the derivative of this function? This is my voice with no alterations.
This is the derivative of my voice.
And this is the integral. You may be asking, how exactly do we take the derivative and integral of my voice, and why does it sound like this? To answer these questions, I must first explain how sound is made up of sine waves. You can theoretically break any sound down to its pure frequencies. The recorded digital signal is the sum of many pure sine wave frequencies present at that time. If we take the derivative of these component parts, then add them all together again, we get the derivative of the original signal. This is true to the sum rule of derivatives, and it works the same way with integrals. The method we use to find pure sine waves of a function is called a Fourier transform.
Audio as a set of single values over time. And if it's periodic at a certain rate, we perceive that as pitch. And how we represent this as data is we take samples at a certain sample. So throughout this project, I was using 44.1 kilohertz. And then, so an audio sample that's 2 seconds would be 88.2 separate data points. And precision would allow you to get different values of amplitude, how loud. And generally, for complex audio signals, this makes sense. But if we were to have something periodic, like, let's say we have an A, so standard tuning, that's 440 hertz, and all we need to represent some note we just heard, like that A, is we need that pitch, and then we need the amplitude and the phase. So at what point in its cycle did we start hearing it? That's the phase. And how loud was it? That's the amplitude. So even 2 seconds of an A, we would need to store just those 4 numbers. Tell somebody the frequency, how long you played it for, the amplitude of the phase, and they can replicate that A. And it turns out, as a general rule, no matter how complex your signal is, it would take only those 88.2 thousand samples could just as easily represent something in the frequency domain. So with no semblance of time, you can represent that same audio signal. And the process for doing this is a Fourier transform. And if you're dealing with a specific number of samples, it's a discrete Fourier transform, DFT. The most common way of doing this is a fast Fourier transform, which is just a specific implementation of that. And a discrete Fourier transform takes all those samples you had, and what it does is it pulls out specific parts of the cycle that are repeating, and longer trends get represented with lower frequency waves, and shorter periods get higher frequency waves. But like I said before, we need at least 3 numbers to replicate a signal, independent of length. So if our x is no longer time and is instead frequency, how this is done is using complex numbers. So since they have 2 values, complex numbers are seen as vectors, and the angle of this vector is its phase, and the magnitude of this vector is the amplitude of that frequency. So Fourier transforms are integrating that signal in time with a specific algorithm. And that's when you're going over all these samples and you're summing them up, you're essentially pulling out the component of a specific frequency. And then the sum of how it's treated across that whole signal in time, compared to what in theory it should be, with that baseline signal, that gives you your value. And then the last important step to being able to perfectly represent a signal is only half your original sample size are the positive frequency values. That's all you need to replicate the signal. And each one of these is a complex number. But then, for a real audio signal, technically you can throw any complex input into a Fourier transform, but for audio purposes, your signal is entirely real. We only had that one value, sorry, didn't have any other component to it. And in that case, you have negative frequency values here that are the complex conjugate of your original one for a real audio signal. So when we're looking to perform calculus on audio, what we do is we really only care about these real values here. But this gives us everything we need to represent something as a wave, and waves are very easy to take the derivative of. So the first thing you need, if you're going to do of the calculus, is to be able to represent the calculus. So some elementary function has a derivative, has a way to take the antiderivative, and that just maps this function to itself. So you define a wave using whether it's sine or cosine, whether it's positive or negative. That's your wave type. Harmonic, because we're in a sort of arbitrary domain, if you do any of these calculations with just hertz, you're going to get extremely inaudible values. And I actually have samples I gave to Simon for that.
This is the derivative of my voice.
Doesn't exactly sound. So what we do is we represent them with respect to some other frequency. So it's a U substitution. And then you have the amplitude and your phase. That's all you need to represent a wave. So we define the derivative and antiderivative of our wave, and then just the algorithms to convert it to and from complex numbers. So since our y values are only amplitude and phase, you have to feed in the frequency to be able to take the derivative. That's all this function does. Too complex is a little interesting. If you actually shift the cosine values to get the real derivative wave, it no longer gives an audible signal. Because, as I said before, you're splitting your domain, and this doesn't treat the sides the same way. It should be operating essentially, have the opposite effect on the phase with those complex conjugates. It just doesn't work. So we have this no shift version that doesn't perform that phase shift that would give us imaginary numbers when we convert it back to audio signal. To actually perform these calculations, these functions here, they give you your relative harmonics and just pair them up with the complex numbers. And these transform functions, there are a few different versions that do a few different things, but they all have that same idea of feeding in the set of values that from the Fourier transform, and then running the operation on the waves themselves. That's this block here. Convert it from complex number, run the function to a complex number, and then spit back out the signal as the complex set of vectors. These are all the different versions of the functions, derivatives, integrals, and then amplitude multiplier here is just so you can get audible signals back out of the integral, because when you do that, you're dividing by incredibly large values. And then this is just the actual implementation. You perform the forward Fourier transform on the sample you read through. So that's time to frequency. You then run your function with whatever parameters you might have for it. There are a couple ones that accept like floor values, and let's only run this on a fraction of them so that if I take the derivative, it doesn't sound like garbage. I didn't actually end up using that because if your fundamental frequency is correct, you're multiplying its amplitude by 1 and it decays out from there. And then to get the audible signals back out, what you have to do is map over this, take the real component of that imaginary number, and then divide by the vector length. That's very important. And that's because when you're doing the Fourier transform, and you're going time, the frequency, back to time, both of these steps are integration. So it's not like going from frequency, you take the derivative, you're summing things up both times. And nobody can agree on at what point you have to reduce those values back down. So the magic number is you have to divide by the signal. So some people say, alright, when we're doing this integration, these are supposed to be inverses of each other, which is why there's debate over this, because Fourier transform to inverse Fourier transform should give you back the original signal. Some people say, alright, divide by 1 over square root on both times. And other people are like, okay, let's just do it on the input side. Because this is what's considered the non-unitary version. So whether you should have the right units up here or the right units down here is whether at what point you divide. A lot of people who are implementing Fourier transforms just don't touch it. So I divide by the signal length at the end. Just do all the computation up here with whatever units they are. Because the amplitude itself doesn't make a huge difference at that point. It's the frequency that needs to be right. And then you can write that to a file with the correct sample rate, and it works. So let's say you have an audio signal. And let's place its fundamental frequency at a nice small 50 Hz. And then there's some higher frequency noise in the background there. 100 Hz, but still the most prominent signal is it. So if you're going off of the fundamental frequency, well actually no, first let's talk about if we just use the units as they are. So essentially with respect to 1 Hz, and you're just taking the relative index in Fourier transform. So 50 Hz, that signal's going to be multiplied by 50 because that's the frequency. You're boosting up your signal by a large margin there when you're taking the derivative. And if you're taking the integral, you're not even going to get an audible signal for most things that are within the range of human hearing. But doing it with respect to the fundamental, it makes these gaps much less drastic. So all you're going to do is that noise is going to background noise, 100 Hz is going to be twice as loud. We're identifying the fundamental by taking the peak in that change of domain. So here's your frequency values. This is the peak, and these do keep the same distance. So a signal that's twice the frequency is going to be twice the distance away from that fundamental frequency. And in fact, if your sample rate equals the length of your signal, n is the standard way to represent that, then each step is going to be 1 Hz. You're going to have that 44.1 thousand bins is what they're referred to as, to catch this frequency value. So this would be at index 50, this would be at index 100. And index 0 is known as DC. So that's 0 Hz. And when you're converting back to the time domain, it's actually somewhat interesting to see how things change. So all you have is this set of values. These are your frequencies, or relative frequencies. These are your amplitudes, and these are your phase shift. You can see a lot of things don't exactly change too much. Like this, just 0 phase shift, pretty basic. And this is just making every amplitude 1. And change that to like 1 over A, you get a much more tame, sawtooth looking signal. But this is what a standard like harmonic set would look like. The derivative, you'll notice, looks pretty much nothing like that original signal. And it's only when you give it some taper off those amplitudes that it begins to have like more of a semblance. and then the integral once it eventually loads. Also looks very different from that original signal. By the way, Desmos, if you're ever using it, hates doing integrals. Because it doesn't, like, check if functions are elementary. I mean, I wouldn't want to implement that either, but it really just approximates.